Well, hello students. We welcome you to our lecture of electrostatics that we have been continuing. In the previous classes, we already finished the topic of area vector and the topic of electric flux. You all know these are important things, very trivial things, but very important things in this topic, in today's topic as well. So let us start it. Today's topic is Gauss theorem. Today's topic is Gauss theorem. So, as you are familiar with electric flux, see, you can be confused with the name. Okay, you can get confused with the name. This is Gauss's theorem, Gauss's theorem, anything you can say. Anything you can say. So this is Gauss theorem, Gauss's theorem, whatever you can say. So what does this theorem speaks about? What do this theorem speak about? Or what does this theorem speak about? So it gives you a relationship. So write it, mind it here. It gives a relation say between the amount of flux through a closed surface and total charge enclosed by. So this is the statement. So what does it speaks or what does it speak? It gives a relationship between the amount of flux through a closed surface and the total charge enclosed by it. So according to this relation, this statement, we can sense that electric flux is phi and charge enclosed by that surface, they are somehow related. They are somehow related. There is some relation between them. There is some relation between them. But this relation is valid when that surface is closed. When that surface is closed. When that surface is closed. So this is the statement. It gives a relationship between the amount of flux through a surface and the charge enclosed by that surface. Okay, so from this statement we get to know that there is some relation between electric flux phi and through a closed surface and the total amount of charge enclosed by that closed surface. So the important condition here is that to apply Gauss's law, we need to, or Gauss's theorem, we need to ensure that the surface is closed. We need to ensure that the surface is closed, just like this. This is a closed surface. I am drawing it on 2D, but when you consider a sphere in space, then it is a closed surface. So it will not work out if the sphere is or if that object is a hemisphere. If that object is a hemisphere, like this. So that at that point, so let me show you something. Okay, let me bring in something. So you can actually imagine a cricket ball, because you have seen it very frequently. It is a closed surface. Okay, it is a closed surface. There are no discontinuity in it. A complete spherical surface. So at that surface, you can actually apply Gauss's law, but you cannot apply Gauss's law in this surface. On this surface, see, it is a part of a sphere. This thing is a part of a sphere. You can actually see it. this thing is a part of a sphere. It is acting as like a hemisphere, not actually or exactly a hemisphere, but it is acting like one. It is not closed from this side. Okay, so you cannot apply Gauss's law for such surfaces. Okay, this was what our statement was. So let us rub it. We are actually going to prove it. This is only the statement. You can actually write it. So you can again remember if that it is only a relation between the flux passing through a closed surface and the total amount of charge enclosed by the by that surface only, by that closed surface only. So when you are writing Gauss's law or Gauss's theorem, you need to make sure that you mention this closed surface. The surface should be closed. This is the required condition to apply Gauss's law or Gauss's theorem. So, what does it give? The statement, it gives a relation between the amount of flux going through a closed surface and the total amount of charge enclosed by that closed surface. By that closed surface. By that closed surface. This is your statement. So, what is that relation? The statement is that it gives you a relationship. But what is that relation? It speaks that flux you can write it from, you can continue it from here. That flux is actually equal to 1 by epsilon naught. You remember epsilon naught? What is epsilon naught? It is permittivity of free space. You have to ensure its value also. It is actually equal to 1 by epsilon naught times. Okay. Not epsilon naught times. 1 by epsilon naught times the total charge enclosed. So this flux is actually equal to 1 by epsilon naught times the total charge enclosed. So mathematically you can write so phi E, since it is electric flux, so you need to write an E at subscript. Phi is equal to, as you know, E dot ds. E is vector field, ds is elemental area, and it is closed. So you put a ring at the integral, or you may write S below the integral. That is equal to, what should be the value of this? Let Q be the charge enclosed, the total amount of charge enclosed into, let me come from the statement, is equal to this much, 1 by epsilon naught times the total charge enclosed by it, or you can write actually Q by epsilon naught. This is your mathematical statement of Gauss's theorem. This is your mathematical statement of Gauss's theorem. So if you understand up to this point, then we shall be proceeding to its proof. So actually we need some space to prove it. So we keep this thing at this side and just rub this whole thing. I assume that you have written all of this. So let us write this statement, mathematical statement of at this point. So phi E is equal to integration of E dot ds, which will give you Q by epsilon naught. Okay, Q by epsilon naught. And this is the thing which we are going to prove. For the sake of simplicity, we are going to consider the simplest system. Okay, we are going to consider the simplest system. This is not that thing that we cannot solve complex system, but complex system is somehow difficult to understand. So first of all, we shall be using a very simple system to understand this concept. So after we prove we prove this Gauss's theorem, we shall be going to understand that why is it necessary. Why is it necessary, or what does the result yield? What does the result of Gauss theorem yield to us? Okay, so let us consider, we can write like this. Let us consider a point charge q. A point charge q. So your charge is q. This is what we are going to prove at a point. That point may be anywhere. Okay, and let us imagine a closed spherical surface enclosing q at its center. So you have been given a point q and you have a spherical surface enclosing q. And where is q? Q is at its center. Q is at its center, or at the center of the spherical. So there is a power cut. So we shall be continuing in just some emergency lights. There is a heavy downpour outside, and we are facing a lot of acute shortages and power cuts. Actually, initially. So let us consider a point charge q at a point. So q is placed at any point in the space, and you are going to imagine a closed surface. You are going to imagine a closed surface, and that sphere is S. That sphere is S with Q at its center. With Q at its center, and the radius should be R, or should be, or whatever you can say. The radius V R. The radius V R. From this point to this point, the radius V R. So what are you going to calculate there? So you can see that if Q is a point charge, we know how to calculate the electric field of a point charge actually. So for a point charge, electric field at a distance r from the point under consideration is given as E equals to, for a point charge, electric field at this surface, at any point on this surface, since on this surface every point is at a distance r from that charge q. So what should be that electric field? 1 by 4 pi epsilon naught q by r squared. This is your electric field. This is your electric field, and this electric field is constant on the surface. At this point, whatever the electric field is at this point, the electric field is same at this point, at this point, at this point, and everywhere. So the same electric field at every point. So this is our equation 1. And now you can actually see, if Q is here, electric field is radially outward. Electric field is radially outward. It points radially outward. Since Q is a positive charge, we are going to assume that Q is a positive charge, and we can see that electric field is radially outward. And at this surface, at this elemental area, if it is an elemental area, you can actually see that the area vector is outside or normal to that surface at that point. So E and area vector ds have this same angle, have this same, or the angle between E vector E and area vector ds is 0. If it is okay. So I am overlapping this thing. So it is ds. So now flux phi E What is that equal to? It is equal to E dot ds. So we can write E ds cos theta. Since it is a dot product, so we can write like this, E ds cos theta, and ds is the elemental area. ds equal to elemental area. Elemental area. So if ds is considered here, then what should be the direction of that surface area at this point? This is here. It is also radially outward. So we can see that so from that observation we can see that angle between E and elemental area ds is 0 degree, which means cos theta is equal to cos 0 is equal to 1. So we replace cos theta is equal to 1 at this equation, which will give us flux phi E is equal to integration over E ds. Since E is constant throughout that surface, E is constant, we can actually take E out of the equation. So E ds is out of the equation and integration is over ds. If ds is the small area, then if we integrate it, the total area is the surface area of that spherical surface. So as we know, it will give us the S, the spherical area. Let the surface area of the spherical surface is S, or you can actually write it like this: ds 0 to 4 pi r squared. Since the surface area of a sphere is 4 pi r square, where r is its radius. So at this point you can write E into 4 pi r squared. If you know something about integration, then you will be actually able to understand why I wrote it like this. When I integrate ds, it will give me S, and S, after putting since it is a definite integral, I put 4 pi r square minus 0. So 4 pi r square minus 0 gives me 4 pi r square, and E is outside of that integral. That means E is in a multiplied form. So we use equation 1 in this equation. So phi E, in place of E, this actual E, we write 1 by 4 pi epsilon naught q by r square multiplied 4 pi r square. This is E. So you just cancel some terms and you will find that phi E is equal to q by epsilon naught. And this was what we were going to prove. This is proved. This is Gauss's theorem. It is quite easy. If you understand small integrals thing, then it is quite easy for you. So this is our Gauss's theorem, q upon epsilon naught. So we have proved Gauss's theorem, hence our Gauss's theorem is proved, hence it is proved. You can actually see from the top right and this from to the bottom, you can actually see the resemblance, that phi E is equal to that integral we have converted into these things. We have actually calculated that integral, we have tried to solve it, and at last we found out that phi E is equal to q upon epsilon naught. This is what Gauss theorem is all about. So we will study a little more about Gauss's theorem, but due to power failure we shall not be able to continue further, and I will upload the next lecture about Gauss's theorem. So this much for today, and let us see you tomorrow. So for if any doubt arises, you can actually drop a mail at the given mail address. I have in my videos, in the lectures, I have given how you can actually contact me if you have any queries. I have also given my WhatsApp there, and for any queries you can add a comment in my videos, and I will make sure that I give you a good response, and we'll see you in the next video. So up until then, practice more, and thank you.